So, let's see. Homework number 7 on chapter 8 is due on the 29th. That's today. Homework number 8 on chapter 9 will be due on the 5th. That's next week, Wednesday. We're going to finish chapter 9 today. We'll have a review of chapters 7 through 9 on the 3rd, Monday next week, and the exam on chapters 7 through 9 on the 5th, Wednesday next week. And we will have a lab today. So, we were talking about center of mass. Center of mass is the point where the system is balanced in a uniform gravitational field. Center of mass is the sum of better one. Oh no, let me do it the other way around. Mass I times xi over the sum of the mass I. For two objects, it's mass of x1 plus mass of x2 over mass of 1 plus mass 2. So it's the sum of mass times position. You add that up for all objects and divide by the total mass. And the center of mass will be closer to the more massive object. It doesn't need to be within the object. It can be outside of it. And the center of mass can move. The velocity of the center of mass is the individual masses times the individual velocities over the total mass. The acceleration of the center of mass is the individual masses times the individual accelerations over the total mass. And the total mass times the acceleration center of mass is equal to the sum of the external forces. And the center of mass accelerates just as though it were a point and particle of mass m, a total mass acted on by force net external. So if you have an air cart with a mass m and a speed v naught, and it moves towards a second identical air cart that's at rest, when the carts collide, they stick together and move as one. Find the velocity of the center of mass of the system before and after the carts collide. So remember, momentum is conserved, momentum initial equals momentum final. So for an inelastic collision like this, that'll be mass 1, velocity 1 plus mass 2, velocity 2 equals mass 1 plus mass 2, velocity 5. So velocity of the center of mass is mass initial, mass times velocity, each one of these divided by total mass. So that's going to be m times v plus 0. So the initial one over m plus m. So the velocity of the center of mass will be v over 2. The velocity of the center of mass final will be m plus m, the total mass times the final velocity over m plus m. Initial momentum equals final momentum. So mass times velocity plus 0 equals 2 times the mass times v final, which is v final equals v over 2. So if we plug that in, we get 2m times v over 2 divided by 2m. We just get v over 2. And so we can see the velocity of the center of mass before and after their collision, where momentum is conserved, does not change. We can also have systems with a changing mass, where if you think about like a rocket ejecting fuel, if a mass of fuel delta m is ejected from a rocket with speed v, the change in momentum of the rocket delta p is going to be delta m times the speed it's ejected. The force or thrust is thus change in momentum over change in time, or delta m over t times v, or the rate at which material is ejected times the velocity it's ejected at. So for thrust, force is delta m over delta t times v. So the ascent stage of the lunar lander was designed to produce 15,600 newtons of thrust at liftoff if the fuel was burned at a rate of 6.4 kilograms per second. What was the speed of the ejected fuel? I'll give you a couple of minutes to work on this. So here, force is 50,600 newtons. I don't know why I keep reading that. Delta M over delta T is 6.4 kilograms per second. And we're looking for velocity, speed. So force equals delta M over delta T times V. So V is going to be force divided by delta M over delta T. So that's 15,600 newtons divided by 6.4 kilograms per second, or 2,440 meters per second. That is how fast the material is coming out of the nozzle, theoretically. So that's the end of chapter 9. So linear momentum is mass times velocity. Momentum is a vector. The second law can be written as delta F equals delta P over delta, is F, sum of all F, F net equals delta P over delta T. Impulse is average force times delta T, and that equals change in momentum. Impulse is a vector. The impulse is equal to the change in momentum. If the time is short, the force can be quite large. If the time is long, the force can be quite small. Momentum is conserved if the net external force is 0. Internal forces within a system always sum to 0. And in a collision, you can assume that external forces can be ignored. For an inelastic collision, kinetic energy is not conserved. A completely inelastic collision is when the two objects stick together afterwards. A one-dimensional collision takes place along a line. In 2 dimensions, conservation of momentum is applied separately to each. In an elastic collision, kinetic energy is conserved. And the center of mass is m1 x1 plus m2 x2 dot 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 over m1 plus m2 dot dot dot, or the sum of all, or m times x over total mass. These are the related formulas for y center of mass, the velocity of the center of mass, and the acceleration of the center of mass. They're all weighted averages, weighted by mass of the relevant quantity. So sum of all mass times y over total mass times velocity over total mass is the velocity of the center of mass, mass times acceleration over total mass is the acceleration of the center of mass. The motion of the center of mass is total mass times the acceleration of the center of mass will equal the net external forces on the system. And for rocket propulsion, thrust is delta M over delta T times velocity. That was chapter 9. Now we have chapter 10, which did not go widescreen as well as the other chapters for some reason. That is just wrong. So let me quickly stop sharing. Share again. I hate that bug. So let's talk about rotational kinematics and energy. So rotational kinematics and energy. So the units of angular chapter 10. We're going to start by talking about angular position, velocity, and acceleration, and then rotational kinematics. So that's, remember back kinematics, that was like acceleration, velocity, and position, those relationships. We're going to do the same thing for rotation. We'll talk about the connections between linear and rotational quantities. We'll talk about rolling motion and rotational kinetic energy and the moment of inertia and conservation of energy with rotation added. So when you add rotation, like when we added springs, we added a second potential energy. When you add rotation, you add a second kinetic energy. So let's start by defining angular position. So the angular position is defined as theta. It's an angle measured from a reference line. So the reference line is, we usually use as a reference like the x-axis, but it's an arbitrary position. The unit is the radian, which is dimensionless. There are 2 pi radians in a circle. The radian is the angle which, with a radius of 1, the arc it draws along the circle has a length of 1. So the radian is actually dimensionless because it's actually basically defined as meters over meters kind of thing. And the convention is, if you're looking at it, counterclockwise rotation is positive, clockwise rotation is negative. We'll go how to deal with it in 3 dimensions. In 3 dimensions, if you're rotating around an axis like this, you curl your right hand in the direction of rotation. Your thumb points in what you would consider the direction of the like angular velocity or something. So this would be positive because it's out of the board. Clockwise would be negative because it's into the board. We're not going to do much in the 3-dimensional stuff because it's messy. We'll deal with it a little later, but it's mainly because it's messy. We're going to mostly stick with just 2 dimensions. You need 3 dimension. You need this sort of definition when you're dealing with rotation, multiple rotations around different axes combining. So the sign convention. Counterclockwise is positive, clockwise is negative. 1 revolution is 360 degrees or 2 pi radians. Arc length. I'm going to erase these. So let's see. So let's see. 1 revolution is 360 degrees or 2 pi. Not the good one. That's the good one. Oh, over there. And you want to figure out the length of arc around the edge of a circle. The arc length measured in meters. Arc length is usually written as S, and it's just the radius times theta. So there's this nice relationship where, because we're working in radians, if we want the arc length, if we want to go to like linear distances, we just need to multiply by the radius. Now, angular velocity, omega, our average omega is delta theta over delta t. So omega angular velocity is d theta dt. The unit, so theta is in units, omega is in inverse seconds, radians per second. I will use radians per second in problems because it makes it clear when you're working. But radians are technically unitless. So this is actually just an inverse seconds. So it's radians per second, which is technically just inverse seconds. Instantaneous angular velocity is the derivative of theta versus time. Unit is still inverse seconds. So, if a wind turbine for generating electricity rotates clockwise at a rate of 17 revolutions per minute, what is its angular velocity in radians per second? So this is a unit conversion problem. We have omega in revolutions per minute. We want to convert it to radians per second. So 1 revolution is 2 pi radians. 1 minute is 60 seconds. So omega is theta over t. So that's going to be 17 revolutions over 1 minute. So that's 17.0 times 2 pi radians over 60 seconds, which is 106.8 radians over 60 seconds, which is 1.78 radians per second. Here we have a CD, rotates through an angle of 106 degrees in 0.860 seconds. What's the angular speed of the CD in radians per second? So just for values, we know omega is 106 degrees. We know the time is 0.806 seconds, and we're looking for omega. And apparently I messed up the image. Trying to do stuff quick. So omega is going to be theta over t. So 106 degrees over 0.806 seconds, but we want this in radians per second. Well, 2 pi radians is 360 degrees, so we multiply by 2 pi radians divided by 360 degrees. We get 1.85 radians over 0.860 seconds, which will give you 21.5 radians per second. This whole section, when we're dealing with radians and degree rotation, is where you have to be very careful about what mode you're calculating. Now, another value we might want to know is how long it takes to make a complete rotation, the period, if something is moving at some speed. Well, the period is just going to be 2 pi divided by omega. 1 revolution divided by the speed. The unit is seconds, time. So period equals 2 pi over omega. And we can also define an angular acceleration. Angular acceleration is alpha. So the average is delta omega over delta t. So alpha is defined as d omega dt. And the unit for this is radians per second squared, radians per second, or just inverse seconds squared, seconds to the minus 2. Now, instantaneous is, of course, going to be that derivative, the limit. You can have, if angular acceleration and angular velocity are in the same direction, your angular speed will increase. They can either be both positive or both negative. But if they're in opposite directions, your angular speed will decrease. So if your velocity is positive, so if your velocity is negative and your acceleration is positive, you'll slow down. If your velocity is positive and acceleration is negative, you'll also slow down. So find the period of a microwave tray that's rotating with an angular speed of 5 revolutions per minute. Oh. Omega is 5 revolutions per minute. And we're looking for the period. The period is going to be 2 pi radians divided by omega. So 2 pi radians over 5 revolutions per minute. So we can convert revolutions per minute to radians per second. So 2 pi radians per revolution over 60 seconds per minute. Multiply that by revolutions per minute. We'll get 2 pi radians over 0.16666 radians per second. Oh, wait. That's, oh, I see what happened. Let me just check something real quick. I might have made a small mistake in writing this up. The answer's right. The period's 12 seconds. Let me just check. 12, 5. Yeah. I made a mistake in this write-up. Let me fix that real quick. We can cancel the 2 pi here. And it would be 1 radian over 0.16666 radians per second, where I'm canceling the 2 pi here and getting 12 seconds. I just made a mistake in that write-up. I'm going to replace these slides anyways, so they'll get updated. You can also think of it as 1 revolution over 5 rotations per minute. So 0.2 minutes, which is 12 seconds. And that's 2 ways you can do the same problem. So a ceiling fan that was rotating with an angular velocity of 12.6 radians per second begins to slow down when it's turned off. How much time does it take for the fan to come to rest if it has a constant angular acceleration of minus 0.168 radians per second squared? Here we have omega 0 is 12.6 radians per second. Our acceleration is minus 1.68 radians per second squared. And our final omega is 0 radians per second. And we're looking for time. So alpha is delta omega over t. Delta omega is going to, so t is going to be delta omega over alpha. So t will be 0 minus 12.6 radians per second divided by 0.168 radians per second squared, which comes out to 75 seconds. So if the angular acceleration is constant, we will get this familiar looking formula. Omega equals omega naught plus alpha t. That should look familiar. If you think of omegas instead as v's and alphas as a's, it might be familiar to you. So if angular acceleration is constant, omega equals omega naught plus alpha t. And in fact, all the kinematic equations that we learned for linear kinematics back in chapter 2, there is an analog where all you do is you replace x with theta, v with omega, and a with alpha. So omega equals omega naught alpha t. Theta equals theta naught plus 1/2 omega naught plus omega times t. Theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And lastly, omega squared equals omega naught squared plus 2 alpha delta theta. Or, oh. So, if the angular velocity of the pulley below is minus 6.43 radians per second at a given time, and its constant angular acceleration is minus 0.491 radians per second squared, what is the angular velocity of the pulley 1.25 seconds later? So I'll give you a few moments to work that out. While that's going on, I'm going to go put these away before I forget. So, basic kinematic problem. Did I screw up? Yep, I forgot to move this to the beginning. So, omega naught, 12.6 radians per second. Alpha, I didn't adjust these. Dang it. I was adding in the starting stuff earlier today. Minus 6.43 and minus 4.91. No, 4.491. And he is okay. So omega naught is minus 6.43 radians per second. Alpha is minus 0.491 radians per second squared. T is 1.25 seconds, and we want to find omega. Omega is equal to omega naught plus alpha t. So omega is equal to minus 6.43 radians per second plus minus 0.491 radians per second squared times 1.25 seconds. So minus 6.43 radians per second, minus 0.61375 radians per second, or minus 7.04 radians per second. Here on a certain game show, contestants spin a wheel when it's their turn. One contestant gives the wheel an initial angular speed of 3.4 radians per second. It then rotates through 1 1/4 revolutions and comes to rest on the bankrupt space. Find the angular acceleration of the wheel, assuming it to be constant. How much time does it take for the wheel to come to rest? Apparently also screwed this one up. So let me freeze this and fix the animation. No, I didn't. Yes, I did. I see. Oh, freeze that. So just materialize our initial angular velocity is 3.4 radians per second. Our the angle we go through is 1.25 revolutions, which is 1.25 times 2 pi radians. Our final speed is 0 radians per second. And we're looking for the angular acceleration and the time. Make it clear that that's delta theta. That's the change in position. I don't remember what I actually used. So we can use this equation, omega equals omega squared equals omega naught squared plus 2 alpha delta theta. So alpha is going to be omega squared minus omega naught squared over 2 delta theta. So 0 squared minus 3.4 radians per second squared over 2 times 1.25 times 2 pi radians. So that's minus 11.56 radians squared per second squared over 15.7 radians, which is 0.736 radians per second squared. So that's part A. Now that we know what alpha is, we can use that in part B. So part B, we're going to use omega equals omega naught plus alpha t. So t is going to be omega minus omega naught over alpha. So 0 minus 3.4 radians per second over minus 7.36 radians per second squared. So minus 3.4 radians per second over minus 7.36 radians per second squared, which is 4.62 seconds. And I'm going to quickly go over these, but I'm not going to do any problems. We're going to finish after I just go over these relationships. So one of the nice things about the relationships between linear and rotational quantities is that if you're using radians, they tie together really nicely. So for example, tangential speed so V tangential just equals radius times omega. And similarly, acceleration tangential equals radius times alpha, like arc length equals radius times theta. And I think that's all I want to cover for today. So we can do the lab a little earlier and get through it. And next week we will have review for the test and the test. So review for the test on Monday and the test on Wednesday. So I'm going to stop the slides and end the meeting.